If you scan the tarmac at any international airport, a strange pattern immediately jumps out at you. On a massive Airbus A350 or a Boeing 787, the engines are slung low beneath the wings, hanging from thick pylons like weights on a barbell. But glance over at the section where the private jets park, a Gulfstream G650 or a Bombardier Global 7500, and the setup is totally different. Here, the engines are tucked away at the very back of the fuselage, hugging the tail. The wings are left clean, uncluttered. So why such a dramatic difference? Then look back a few decades and you'll find an even stranger sight: airliners with 3 engines. The Boeing 727, the DC-10, they carried 1 engine under each wing and a third buried in the tail, its intake gaping open like a second mouth. So what's going on here? Why do planes that all do the same thing, fly, look so different under the hood? In aviation, almost nothing is an accident. Every curve, every angle, and especially every engine placement is a calculated trade-off. It's a tug of war between the laws of physics, the need for profit, and the absolute demand for safety. To crack this code, we have to start with the engine's real job. A jet engine is a thrust machine. Its only mission is to shove the plane forward through the air. It's the wings that actually do the lifting, sculpting the airflow to generate the force that gets you off the ground. So the engine's position isn't about lifting the plane, it's about managing that thrust. What happens when one of those thrust sources suddenly quits? You get an immediate imbalance. The plane wants to yaw or swivel towards the dead engine. The pilot fights this with the rudder, a massive vertical fin designed to counteract that force. This is the invisible hand of engine placement. It dictates how hard that fight will be. And that brings us to the first big constraint, the center of gravity. Think of the plane as a giant seesaw. The wing is the pivot point. For stable flight, the plane's center of gravity, the point where all its weight balances, must sit just ahead of the wing's center of lift. This creates a natural, self-correcting stability. Now, modern jet engines are monstrously heavy. A Rolls-Royce Trent XWB, the kind that powers an A350, weighs several tons. If you bolt that kind of mass way back on the tail, you're yanking the seesaw's balance backwards. The nose wants to pitch up constantly. Engineers then have to fix this by adding more weight to the nose or making the tail surfaces bigger and heavier, which creates a vicious cycle of inefficiency. The golden rule? Put the heaviest stuff as close to the main load-bearing structure as possible. On most airliners, that's the wing. This is the core reason you see engines under the wings of planes like the 737 or A320. The wing isn't just for lift, it's the plane's structural backbone. Inside is the wing box, a reinforced skeleton of spars and ribs designed to handle immense bending forces. By hanging the engine on a pylon from this strong box, you're using an already robust structure to carry the load, avoiding a major reinforcement of the entire fuselage. In fact, in flight, the wings naturally want to flex upwards. The weight of the engines hanging below acts like a counterweight, pulling down and actually reducing the bending stress at the wing root. It's a clever piece of engineering where the problem helps create the solution. But there's another, simpler reason. Look at the size of a modern engine. To be fuel efficient, they've gotten enormous with massive fans at the front. The fan on a GE90 is barely smaller than the fuselage of a regional jet. You simply can't fit something that big on the tail of a full-size airliner without it looking absurd and causing massive aerodynamic interference. Under the wing, it has room to breathe. There are practical perks, too. The fuel is stored in the wings. Mount the engines right below them, and your fuel lines are short, simple, and in an emergency, fuel can even gravity feed into the engines. Maintenance is a breeze. Technicians can stand on the ground and work instead of needing scissor lifts and scaffolding. This speed of service saves airlines millions. But it's not a perfect world. The underwing setup has its own headaches. Ground clearance is a constant worry. As engines balloon in size, engineers have to design taller landing gear just to keep the intake from scooping up tarmac. And being low to the ground makes them vulnerable. They can suck up debris from the runway, stones, ice, chunks of rubber, a phenomenon called foreign object damage. That's why airports are obsessively cleaned. And remember that yaw problem we mentioned? When an engine fails on the wing, it's way out on the side, creating a massive turning force. To counter this, the plane needs a gigantic vertical stabilizer, which adds weight and drag. Plus, the thrust itself affects pitch. Add power, and because the engines are below the center of gravity, the nose lifts. Cut power, and the nose drops. It's a coupling pilots have to constantly manage. So, the underwing setup is a compromise, the best one we've found for big, efficient jets. But it's not the only answer. So why do business jets and regional planes stubbornly stick with tail engines? The tail-mounted engine offers a completely different set of trade-offs, perfectly suited for smaller aircraft. The biggest win is a clean wing. Without a heavy engine and pylon disrupting the airflow, the wing performs more efficiently, especially at the lower speeds these aircraft often fly. It's an aerodynamic advantage that's too good to pass up. Protection from debris is another huge plus. Sitting high and behind, these engines are far less likely to ingest grit from a rough regional runway. For a plane that hops between small airports, that's a major reliability boost. And for the executives inside, comfort is key. A huge amount of jet noise radiates backwards from the exhaust. By placing the engines behind the passenger cabin, that noise is directed away, making the ride significantly quieter and more serene. It also unlocks better short-field performance. With the wing clean of obstructions, engineers can fit larger, more effective flaps across the entire trailing edge, giving the plane more lift for shorter takeoffs and landings. There's also a sneaky practical reason. Many business jets have built-in air stairs. To keep those stairs a reasonable length, the fuselage sits low. There's no room under the wing for a giant engine, so it gets moved to the back. Some, like the MD-80, can even use their tail-mounted engine thrust reversers to push back from the gate without a tug, a neat party trick. But these perks come at a cost. The engineering gets more complex. Fuel must now travel all the way from the wing tanks to the tail, requiring long, heavy lines that snake through the fuselage. The balance shifts dramatically. With the heavy engines in the back, the center of gravity moves aft. Engineers have to carefully ballast the front of the plane with heavy equipment just to get the seesaw balanced again. The pitch behavior also reverses. If the engines are mounted high, adding power tends to push the nose down, the opposite of an underwing plane. And then there's the notorious T-tail. Because the horizontal stabilizer is often placed on top of the vertical fin to keep it out of the engine exhaust, it creates a risk called a deep stall. If the plane's nose goes too high, the turbulent air from the stalled wing can wash over the tail, rendering the elevators useless. To prevent this, these planes are often equipped with a stick pusher, a system that literally shoves the control column forward to force the nose down before it's too late. It's a safety feature born directly from the engine's position. But there was a third way, a weird, wonderful, and now nearly extinct configuration. The trijet. In the 1960s and 70s, engines weren't as reliable as they are today. Regulations demanded that if you were flying over the ocean, you needed to be able to lose an engine and still have enough power to reach an airport. This meant twin-engine jets were restricted to routes where they were always within a certain distance of a diversion strip. For long-haul, airlines needed redundancy. They could go with 4 engines, like the 747, but that was expensive. The compromise? 3. The trijet, like the majestic McDonnell Douglas DC-10, offered a middle ground. It had the redundancy for ocean crossings, but was lighter and more economical than a 4-engine behemoth. It was the perfect solution for its time. The third engine was typically buried in the tail with a serpentine S duct feeding air to it from an intake on the fuselage. It was complex, but it worked. So, what killed the trijet? Reliability. Jet engines got so good that failing became a statistical anomaly. At the same time, regulations caught up with technology. The ETOPS rules were introduced, allowing incredibly reliable twin-engine jets to fly any route, any time. If an engine is virtually guaranteed not to fail, why carry the weight and fuel burn of a third one? The trijet's advantage vanished overnight. Looking across the history of flight, you see the same story repeated. Engine placement isn't a stylistic choice, it's a fingerprint of the mission. It's a crystal-clear snapshot of the trade-offs engineers were willing to make. In aviation, form doesn't just follow function, it is forged by it. That's why the A380 has 4 massive turbines under its wings, and a Citation Mustang has 2 tiny ones on its tail. Every configuration is a perfect answer to a specific set of questions about physics, profit, and risk. The next time you're at an airport, take a second look. That engine placement isn't random. It's a story. A story written in titanium and aluminum, a silent declaration of the aircraft's purpose, born from a century of hard lessons and precise engineering. It's a story that allows millions of us to fly safely every single day. If you enjoyed this deep dive into the hidden logic of flight, hit that like button to help others discover winds of thought. And now, I'm curious, if you could design a plane, where would you put the engines and why? Let me know in the comments.